Alright, in the last video I introduced simple harmonic motion and kinematics and kinematic equations. This time I want to talk about a few terms, forces on a mass that is in simple harmonic motion, and perhaps energy if time permits. So I've used a couple of these terms already, and now I'd like to discuss what they mean and where you can see them. So first is amplitude. We represent that with the letter A. That is measured usually in meters or possibly centimeters, and it is the distance away from equilibrium that the mass is at its maximum displacement. So this is maximum displacement away from equilibrium. And that is represented on the graph over here by this distance A in the x versus time graph, or negative A when the mass is below equilibrium. Keep in mind that because it is a displacement, there's going to be the positive on the one side of equilibrium and the negative on the other side of equilibrium. And in either case, the object is going to be pulled back towards equilibrium. And it will reach back past equilibrium and begin to repeat its motion after one period. So this is a specific time, the time that an object takes to begin repeating its motion. And we represent that with a capital T. That's usually measured in seconds. Now, again, that capital T is a special time. It is not the variable time. And for any given mass on a given spring, that big T, that period, is not going to change. Frequency is how many cycles of repetition a mass goes through per second. We use the variable lowercase f, and that is measured in 1/seconds or hertz. HZ is the abbreviation for hertz. Yes, that's hertz, like the car company, like the rental car company. And then there's angular frequency, which is frequency times 2 pi, that we need to use inside the trig functions. So this is also known as the angular speed. And this is where circular motion really comes in, because angular speed that we've already talked about, omega, and that is measured in radians per second. The first thing, amplitude, that's a distance, but these three guys, notice that they have time as part of their measurement. So there's a relationship there between period and frequency and angular frequency. Period and frequency, if you take a look at the units, they are reciprocals of one another. So 1 over the frequency is the period, and 1 over the period is the frequency. And to get from frequency to angular frequency, notice the only difference between these two guys is that we've now multiplied this by radians. So having multiplied it by radians, omega is going to be 2 pi times the frequency. But since frequency and period are related to each other, we also call it 2 pi divided by the period, since period and frequency are reciprocals. Keep these relationships in mind for what we're going to do next. We're going to look at forces on simple harmonic motion. We're going to put a block of mass m on a smooth table, and we're going to have one end of the block, one side of the block, attached to a spring, and then the other end of the spring is going to be attached to a wall. And for mathematical simplicity, let's keep that spring to be ideal and massless. Now, an ideal spring, ideal Hooke's law spring, is one in which the force generated by the spring is directly proportional to how much that spring gets stretched. So if I pull this mass to the right by 1 centimeter, the spring is going to produce 1 centimeter's worth of pullback. If I pull it over by 2 centimeters, then it will produce 2 centimeters of pullback, and it will be directly related to how stiff that spring is. And you saw that at the beginning of the previous video, where I put 2 different masses on 2 different springs, and those 2 different springs generated different amounts of force based on the amount of stretch that they had. So the equation that we have here for Hooke's law spring is the amount of stretch scaled according to how stiff the spring is, and the direction will always be opposite the displacement. So if I displace the mass to the right, so it has positive, the spring will pull negative to the right, also known as the left. But if instead I push the spring in, so I'm displacing it to the left, then I will have a negative x, and a negative times a negative will give me a positive when I multiply them, and that means the spring will be pushing it to the right. The point of the spring is to undo whatever you just did to the mass. So if I pull this mass to the right, let's take a look at the free body diagram on that mass. It's sitting on a table, so the table is going to push up on it, and gravity is going to pull down, and the spring is going to pull to the left. Now, notice that I've already dealt with the direction here in my free body diagram. Since I've dealt with the direction, I don't need the negative sign. The point of the negative is to tell you about the direction. So this force is going to be kx. It's not going to be negative kx. If you put the negative in there, it will be the negative of the arrow, which will claim to be to the right. So don't double dip on your negatives. This arrow took care of that negative. The negative is the algebraic equivalent of the let's draw the arrow to the left. Now that we have a free body diagram, let's use Newton's second law to analyze the motion of that mass. Previously, we did a kinematics analysis of the mass, and we ended up with some kinematics graphs, and then the kinematics equations to go along with the graphs. Now let's use Newton's second law, and our goal is to end up with a usable equation to describe the motion of the block. So we're going to start with Newton's second law here and add up all the forces that cause the mass to accelerate. And if you take a look at our free body diagram, the normal force and the weight are going to cancel each other out, and the motion of the mass is going to be left and right. But because we put the block on a smooth surface, we don't need to worry about friction. That's the entire reason for putting it on a smooth surface and having it go sideways, whereas previously I had it going up and down. If I continue to have it going up and down, I would have to deal with gravity, and I don't want to do that. So to make the math easier, let's figure out a way to ignore gravity by just making everything go sideways. So we're going to look at the forces only in the x direction. Well, only in the x direction, we only have this guy, kx. So kx, and for right now, I need to say, well, I've displaced it to the right, so I need a negative there. Again, the negative is the algebra. The arrow is the same thing. And that spring is going to cause the mass to accelerate. Well, how is the acceleration related to these other guys here? Well, k, that describes the spring. That's not going to change. That's just a number. M, that describes the mass. That's just a number. X is the position, which is going to be changing in time, and A is the acceleration, which is also going to be changing in time. Turns out that the acceleration is related to position by being a negative constant times position. We derived that in the previous video with kinematics. This is a kinematics relationship. You can get that at the end of the previous video. So let's substitute that guy into here. And we're going to have a very happy thing happen. The minus signs are going to cancel out, and the x's are not going to get to cancel out. So we're going to get to remove those guys, and those guys, and those guys, and those guys, and we're going to be left with k equals m omega squared. Where I started with this video is in some definitions and relationships among period and frequency and angular frequency. And we're going to be able to get rid of this omega squared and put it in terms of something that we can measure with a stopwatch very easily. Remember that omega is 2 pi over the period. And if we square the omega, we just put squares on all of these guys. And now we can get rid of the omega, the angular frequency, and replace it with the period that we can just measure with a stopwatch. So let's put these two guys together, and we'll have k equals m 4 pi squared over t squared. Now that's not the normal way of writing that equation. The normal way of writing that equation puts the t all by itself and everything on the other side. So let's do that. All right, now that relationship, t equals 2 pi root m over k, is one that, yes, it's good to memorize, but you also need to be able to reconstruct this for springs in slightly different contexts so that you're going to end up with slightly different equations at the very end. Which is why I'm showing all of this from the beginning to the end. You need to be able to reconstruct this, starting with Newton's second law, and then substitute in the exact spring that you were given so that you can end up with the relationship for that spring. This is a general solution that applies to the situation where we have the ideal Hooke's law spring. All ideal Hooke's law springs act like this. However, not all springs are Hooke's law springs. So since not all springs are Hooke's law springs, you need to be able to reconstruct that for non-Hooke's law springs. What does this equation tell us? First, it tells us that if the mass gets bigger, the period will also get bigger. So the bounce of the mass on the spring will get slower. It will look slower. It also tells us that if the spring is replaced by a stiffer spring, meaning K gets bigger, then that means the mass will bounce faster. The period will be reduced. Let's write that down. If the mass gets bigger, then it will slow down in its bounce. But if the spring constant gets bigger, meaning it's a stiffer spring that's harder to stretch or compress, then that will speed up the bounce. It also tells us that there's a square root in there. So the amount that the mass gets bigger, you have to take the square root of that. We will take a look at how to analyze the data on a Hooke's law spring to produce a straight line graph. We'll do that at some other time. In the next video, I will take a look at the energy transformations inside a spring for a mass undergoing simple harmonic motion. And then I will look at an example problem putting numbers to all of these things with the kinematics and the forces and the energies for a mass undergoing simple harmonic motion.